Hello, wonderful people. Hi, hi, hi. So here we are in what chapter? 32, electrostatics. Should have had that written down there. And now we are on section 32.3, Coulombs Law. So, first things first, there is a glass rod and I'm rubbing it across the silk. And as I do that, the electrons from the glass rod get left behind on the silk. There's one, there's another. So there's the electrons getting left in the silk, and the atoms that are still in the glass rod are missing electrons, so they have a positive charge because they have more protons than electrons. And everything adds up. See that? 5 positives and 5 negatives. Sorry, 5 positives and 5 negatives. That adds up to 0. And that's where we were at the start of this. There's 0 charge on the silk and the glass rod, and there's still 0 charge on the silk and glass rod. If you add them together, there's 0 there, 0 there, and 0 there. 0 there, 0 there, 0 there. Why? Because if you add a positive and a negative, you get 0, right? So that's the point. Charge is conserved. The law of conservation of charge says the total electric charge in an isolated system never changes. So isolated system, that just means that there's my isolated system, the silk and the glass rod. Now, if we started, let's say, and I had a bunch of extra electrons already on the silk, like, I don't know, 5 negative electrons on the silk, then if I add one more to the silk, the total will still be -5, still -5, still -5. So whatever charge you start with in a situation, such as the silk and glass rod, is the charge you end with, because the law of conservation of charge says that the total charge never changes. Now, you can make an electron go somewhere else, but that leaves behind a proton somewhere, right? Does that make sense? I hope so. So that was actually 32.2 for those of you who are following along in the book. I didn't number that because I'm just tacking that on today. And then today goes into section 32.3. So here is Coulombs law. There's the equation for it. It says F equals K times Q1 times Q2, all divided by R squared. Now what's that telling us? So let's make the situation. Coulomb's law is telling us that if you have a bunch of electrons on one thing and a bunch of extra electrons on another thing, those electrons, we know, are going to create a force that are going to push each other away. So the question is, how strong is that force? And that's what Coulomb's law is answering for us. F for force. It's going to tell us how much force you get out if you have a certain amount of charge on Q1 and a certain amount of charge on Q2. Now, how do we measure charge? We count the electrons. And remember, we don't count electrons by dozens, we count electrons by coulombs. A coulomb is 6 quintillion, 400 quadrillion, that huge number. But it's just a number, and 1 coulomb of charge represents that number of electrons. So that's all we're doing. Q1 is the measure of charge. How many coulombs of electrons are there? And how many coulombs of electrons are on Q2? You take those two numbers and you multiply them together. Now, if these two things, Q1 and Q2, are a distance apart, then you take that distance, R, and you square it. Do you remember the gravity equation? The force of gravity goes down the further apart two things get, and it's because it's divided by the distance squared. It's the same idea here. The radius, the distance between the two things, squared. Then the weird thing about all this is the K term. K for constant. And there it is. K equals 4 pi times E. That's actually a Greek letter. I forget which one. Lowercase sigma. Sub-0. That's a subscript. And all that is to the -1, 1 over that number. And E sub 0 is called the permittivity of free space. Don't worry about that name. It's just a number, 8.86 times 10 to the negative 12. And then the units on are a little weird. Coulomb squared divided by newtons times meters squared. And the point of that K is to make the units all work out. So when you multiply Q1 and Q2 and divide by R squared, and R is going to be measured in meters, then the K is designed so that all that comes out with units left over in force, because that's how force is measured in, do you remember? Newtons. Newtons are the unit of force. So let's do an example. Oh, before we do the example problem, I wanted to just show, oops, pushing the wrong button. I want to show you the gravitational force equation. Some of you might remember this from back in September, October. The force of gravity equals G times M divided by R squared. And in this case, the M's are the mass of the two things. So we did an example where we did the mass of the sun and the mass of the earth way back in September. But right now, we're going to use an example where we take the mass of the proton and the mass of the electron. So the electron orbits around the proton, and that's the picture you see there. You see that little showing the orbit that it's going around. And then there's the proton, and the proton has a mass of 1.7 times 10 to the minus 27 kilograms, because they're very, very tiny. And then the mass of the electron is 9.1 times 10 to the minus 31 kilograms. The distance between them is 5.3 times 10 to the minus 11th meters. That's about how far the electron is from the proton in an ordinary hydrogen atom. And then the constant G, that's a conversion constant. And if you multiply all those things together, you get an answer of 3.6 times 10 to the minus 47. So that's the force that gravity is pulling between the electron and the proton. Now let's do the same for the electrical force. The electrical force in the proton is plus 1 charge, and the electrical force in the electron is minus 1 charge. So you plug those into the Q, the distance is the same as before, and then you use the K for constant, and you get this answer. Now, I'm not asking you to follow along in any of that math. This is what I'm asking you to notice. The force of gravity is something times 10 to the minus 47. The force of the electrical attraction is something times 10 to the minus 8th. Yes, 10 to the minus 8th is very small. But how much bigger is it than 10 to the minus 47? It's about 10 to the 39 times bigger. The force of the electric force between the proton and electron is 1 followed by 39 zeros times bigger than the gravitational force. That's weird that it is that humongously different. So I would just like you to think about this. That means that the Earth, in order for the Earth to make gravity, has to be enormous, as big as the Earth, right? And it doesn't make a whole lot of gravity. I mean, we feel it here, but we can jump up and down. The force of the electrical charge between those two things is just so much stronger than gravity. So that means that you don't need a whole lot of electrons to make a sizable force. That's the point of that, just to point out that fact. In comparison, the electrical force is much stronger than the gravitational force. Okay. Now, I should have done that after this example, now that I think about it. But here we go. We're going to do an example problem for Coulombs law. So there's the problem. Suppose the 2-point charges, each with a charge of 1 coulomb, are separated by a distance of 1 meter. Determine the electrical force of repulsion between them. So I write down what I'm given from the question. I have a charge of 1 Coulomb on both Q1 and Q2, and the distance between them is 1 meter. And it says determine the electrical force. So I'm trying to find the force. So I move that stuff up to the top of the screen. There's the equation I'm going to use. The force of the electrical force equals K times Q1 times Q2 divided by D squared. That was just the same equation from way back right there, right over there. Okay? Now, I'm going to plug in those numbers. I have K is 9.0 times 10 to the 9th times newtons times meters squared divided by Coulomb squared. That's K. Q1 is 1 Coulomb, and Q2 is 1 Coulomb. And then divided by 1 meter, don't forget, squared. Now, I'm not going to go through the math of 9 and 10 to the 9th and all that. I am going to show you this. The coulombs, there's the C for Coulomb, that cancels with the Coulomb that's underneath the divide by sign here. And that other Coulomb cancels with the other C because it's squared. So those two C's go away. So I'm just eliminating the units that I can cancel in here. Does that make sense? Do you see what else we can cancel? This meter squared, where's my pointer? This meter squared can get canceled by this meter over here that's underneath the divided sign. So I cancel that meter squared with this meter squared. Then I just multiply all the numbers through, and it's 1 divided by 1 times 9 times 10 to the 9th. So the force between those two things is 9 times 10 to the 9th. That is a billion newtons. 9 billion newtons. Do you know how much force that is? So how much force is 9 billion newtons? Let me show you. That's a picture of the Saturn V rocket being launched right off the pad. You can see the rockets in the very bottom. There's actually 5 of them. They're all on the bottom of the rocket. It's a little hard to see there. Each one of those nozzles, that's the word I'm looking for, produces 7 million newtons of force. So 7 times 5 is 35 million newtons of force to lift that whole rocket up and launch it up into the air. There you can see the shock wave on the nose cones. So that's 35 million newtons, and the answer to our equation over there is 9 billion newtons. So there is 35 million newtons pushing a rocket up into space, and now you can start to see the 5 nozzles on the bottom of the rocket a little better. And our answer is 9 billion. So that's a lot of force, right? And when I said that we're given with 1 Coulomb of charge, 1 Coulomb is not that many electrons. You'd be surprised. Like if you have several lights turned on in your house, that is 1 Coulomb of charge flowing through those lights per second. Just to try to put it in perspective. It's not hard to get 1 Coulomb of charge together. Now, what is hard is to get it together and hold it in place and then try to push it against another force somewhere nearby. I mean, if you could not just set up these two, Q1 and Q2, to launch the rocket, if that's what you're thinking. So that gives you an idea of how strong these electrical forces are. Okay, so there's the equation. I'll take off those marks. You plug in the numbers, you do the math, you cancel your units, and you get an answer. And that's what I'm going to ask you to do in the homework. There's just a few questions, a couple solve the problems just like this to get used to it. And then that'll be good for today. So remember, C for Coulomb is just a count of how many electrons there are. And I think the rest was pretty straightforward. If you need anything, please don't hesitate to ask. Thank you so much. Bye-bye.